All right, everybody, welcome back to chemistry class. Today we're going to continue our study of the gas laws, and we're going to be looking at two different variables today, pressure versus temperature. Now, we've looked at pressure before, and that was in Boyle's law, where we looked at what happens when the pressure and the volume, we looked at the relationship between those two characteristics. Now we're looking at pressure and temperature. And so this is the third law that we're studying. And this law, the name of it is the Gay-Lussac Law, named after Joseph Gay-Lussac, who studied this aspect of gases. So let's get into it. All right, so definitely today we're going to need to talk about exactly what pressure is, okay? So basically, in the easiest way to think of pressure is going to be the number of collisions that gas particles have with the walls of the container they're in. Okay? So I want you to imagine if you had a balloon, okay, so here's your balloon, and you had some gas particles. I'm just going to have 3 of them in here. These gas particles, we know according to the kinetic molecular theory, are always moving. And so when they hit the side of the container, they're going to kind of push on those walls, and they're going to create what we call pressure. Now, the thing about pressure is that you can change pressure by increasing or decreasing the amount of collisions that happen. And there's a number of ways to do that, okay? Instead of having 3 gas particles, maybe you could have 3,000 gas particles. That would definitely make more collisions and the pressure would be higher. But if you think about the kinetic molecular theory, there are other things that you can do to make these particles hit the side more often. And that's where we start to talk about temperature, okay? Now, just a little refresher course. Remember that temperature is just the average amount of kinetic energy that a material possesses. So in the case of the gas, it would be just how fast these particles are moving, okay? And so think about what this means. So if we have high kinetic energy, I'm going to just call it kinetic energy, that means that the particles are moving fast. And the same is true in the opposite direction. If you have low kinetic energy, that means the particles are moving slow. So now, what is high kinetic energy? Well, we would call that high temperature, okay? So if you have something that's hot, a gas that has been heated up, then those gas particles are moving very fast. And I want you to think about what they're going to do to the walls of that container that they're in. They're moving so fast that they're probably going to hit that container, the walls of that container, more often and with more force. And that would mean that the pressure would increase. Okay? So if we were going to look at it like this, it would be like high kinetic energy means faster particles, okay, which would mean more collisions, which would mean higher pressure. Now, when I say more collisions right here, you have to remember that those are collisions with the walls of the container. And one thing about this container is that it has to be a rigid container. It can't change volume. because if it was like a balloon and you were heating up the gas in a balloon, well, the size of the balloon would just get larger and larger, the volume would increase, and the pressure would pretty much stay the same because the volume's getting bigger. But as long as you have a container that has a fixed volume, what you can see then is that there is, and I'm going to put it here for you, a direct proportional relationship between pressure and temperature. Okay? And so this is what we would call the Gay-Lussac Law. Joseph Gay-Lussac studied this, and he determined that there is a directly proportional relationship. Now, what does that mean? To be directly proportional, it would tell us that if you increase the temperature, you increase the pressure. If you double the temperature, you double the pressure. Now, the opposite of a directly proportional relationship would be an inverse relationship, like Boyle's law, where if you change the volume, you're going to half the pressure. Like if you increase the volume, you decrease the pressure. It's the opposite. Okay, but not this law. This law is what we would call directly proportional. So let's write down what the mathematical, how this looks mathematically. Okay, so let's do it like this. Okay, so here it is. We'll make a nice little arrow. Okay, so here we go. P1 over T1 is equal to P2 over T2. Okay, and this is going to be the formula we're going to be working with for Gay-Lussac's law. Okay, now P1, of course, is the initial pressure. And if you forgot pressure units would be like atmospheres, kilopascal, torr, millimeters of mercury. This is just a review. Those are all pressure units. T1 is going to be the initial or starting temperature. Okay, and this has to be in, guess what, guys? Kelvin. Okay, and so very important that you change the temperatures for these things into Kelvin for this law. Okay, all right, let me just highlight a couple more things here. There we go. All right. Now, what about P2? Well, P2 is just going to be the final pressure, and I'm not going to put down the units again. I think you can kind of figure that out. And then T2 is going to be the final temperature. And so, like always, if you're given 3 of the variables, you should be able to solve for the 4th one. Okay? All right, so what we're going to do now is we're going to take some time to work 2 of the most common problems that you would see with this, law, okay? And we're going to solve these problems the same way that you've solved the other problems, okay? In fact, we do that pretty much with all the problems that we come up with from here on out in chemistry. So what you're going to have to do is read the problem and determine which law to use. You have 3 choices: Boyle's law, Charles' law, or the Gay-Lussac law. And then you're going to write down the formula you're going to use, and then write down what you know, and then plug in the values, and then solve. All right, so let's do these 2 examples right now. All right, so here we go. we are given that it is known that let's get the highlighter here, so make your life a little easier. We know the pressure of a gas, okay, is 3.20 atmospheres. All right, so let's write that down. So that seems like what we're starting with. So the pressure, P1, is 3.20 atmospheres. Okay, that's pretty good. Now, and that is at 22 degrees Celsius. So that would be the temperature that is at, all right? So 22. Now let's convert that directly into Kelvin. Notice how I just do it right away, right? Don't wait. And so 273 plus 22 is 295 Kelvin. Okay, so there's the value we're going to use. And now if the temperature rises, okay, so the temperature rises, that means it changes to 60 degrees Celsius, remember, plus 273. Do the conversions quickly, so you don't do them immediately, so that you don't make a mistake and forget to convert them. What will be the gas pressure? Okay, so the gas pressure has changed. So what will be the gas pressure? So you're solving for the new pressure. So that's going to be P2. All right, so what's really nice about this problem is you have the temperatures are both in Kelvin, and the pressure unit is in atmospheres, so that means that you're going to end in atmospheres. So let's set it up. Now, I didn't write down the formula. I should have done that. I'll do it now. P1 over T1 is equal to P2 over T2, okay? You definitely want to write down the formula, though, so you know where to plug in the information, right? So P1 is going to be 3.20 atmospheres, and then T1 is 295 Kelvin, and P2 is unknown, and T2 is 333 Kelvin. Okay. All right, so we have two fractions with an equal sign, so we can play our little cross multiplication game, right? So when you multiply 333 times 3.20, you get 1065.6 atmosphere, don't forget the Kelvin, times Kelvin, is equal to, now look, if you do it that way, you can cross multiply this way as well. And so that comes out to be 295 Kelvin times x. Just like all the previous problems we've done, right, guys? Okay, so now you're going to do a little division here to get the 295 Kelvin out of there. Do it on this side as well. Okay, there's your equal sign. Cancel, cancel. So that leaves you x. Look at this, the Kelvin's gone. Kelvin's gone. Atmosphere is all we have left. Let's do the math. 1065.6 divided by 295 gives us a value of 3.61 atmospheres. Okay, so let's look at the problem. So what will be the gas pressure? All right, so what did we do? We took the temperature from 22 to 60. So that's raising the temperature. That's increasing the amount of kinetic energy, meaning that the molecules are moving faster and they're hitting the walls of the container more often. And because of that, the pressure should be going up. It should be larger than 3.20. This is what it started at. And what did it end at? 3.61. So the pressure increased, just like the Gay-Lussac Law predicted, okay? Predicts. All right, sometimes I have trouble speaking, but I think you understand what I'm saying here. The pressure went up. So there is the solution to the first problem. Now, every other problem is just basically the same. You're going to see, the same type of solving. You're going to see this again. You're going to see this again. You're going to see that again. The math is even the same, all right? But let's do another one because you may run into something like this. Let's solve for something different, okay? So here's problem number 2. All right. So if a gas sample has so pressure, so P1, of 15.5 kilopascals. Don't let that worry you. It's just a pressure unit. And that's at temperature of 10 degrees, so T1. So it starts at 10 degrees Celsius plus 273 equals 283 Kelvin. Okay? So what else? Okay, by how much does the temperature have to decrease to lower the pressure to that? Okay, to lower the pressure. Okay, so that must be P2, right? 2.50 kilopascals, okay? And then look at this, by how much does the temperature have to decrease? Okay, so we probably should get then T2. It's the only thing we can solve for. But our answer is not going to be the ending temperature. It's going to be the difference between T1 and T2, because notice they want to know by how much does the temperature have to decrease. So don't get worried about that. We'll figure that out when we get there. But let's solve for T2 right now to see what the new temperature has to be for the pressure to be decreased to 2.5 kilopascal. All right, so once again, I didn't put in the formula, and I think that's probably because sometimes I like to see what I have before I decide which formula to use, okay? And so here we go. Let's do the game again. So P1 is 15.5 kilopascal over T1, which is 283 Kelvin, is equal to P2, which is 2.50 kilopascal. And look at how nice it is that both units are the same, kilopascal. That means that they're going to cancel out. And then that's over T2. So that's what we're solving for. Okay, so let's do it. So we can do this. Okay, there we go. So 15.5 kilopascal times T2 is equal to, now let's do some math here, 283 times 2.50 is going to be 707.5 Kelvin, right, times kilopascal. See that? Kelvin times kilopascal. There it is. All right, so now we're going to have to divide. It's the same game again, guys. Looks like something we've done before, because it is. Okay, 15.5 kilopascal. This is gone, leaving us T2, okay? And then look at this, the kilopascals, they're gone. So the only unit we have is Kelvin, so we're going to just put that there. All right, so 707.5 divided by 15.5 comes out to be 45.6 Kelvin. Now, that's what the temperature has to be in order for this pressure to exist. But look at the problem. The problem says, by how much does the temperature have to decrease? So we're going to have to actually take the starting temperature and subtract the ending temperature, okay? So if it starts at 283 Kelvin, we're going to subtract 45.6 Kelvin, so we know by how much it has to decrease, you see? If you just put down the answer as 45.6, you'd be wrong, because that's not how much the temperature has to change. That's what the temperature has to be at the end. A little tricky, right? So here we go. Let's do subtraction. So 283 minus 45.6 gives you, oh my goodness, 237. I've rounded that to 3 sig figs, Kelvin. And this is actually the answer, because what this is the amount that the initial temperature, remember the initial temperature was 283, right? This is the amount that the initial temperature must decrease, okay? And that's what they wanted right here, all right? You see that? they actually want you to tell them, how much does it have to decrease? Now, why am I telling you that? Why am I spending so much time telling you that? Because you really have to be on the game here so that you are aware of what you're solving for. Sometimes in the solutions in the book, you might come across 237 and you're like, no way, the answer is supposed to be 45.6. But you have to be careful so that you can see that they're actually asking for the amount it has to decrease. Okay, guys, so what have we done today? Well, we talked about the definition of the Gay-Lussac Law. We talked about how pressure and temperature are related, directly proportional. And we also actually talked a little bit about how you can use the kinetic molecular theory to predict what's going to happen if you change the temperature on a gas sample. All right, we've also done 2 problems here that you can use in your homework tonight to help you solve the 3 book problems that you're going to have for your homework, okay? All right, guys, we will go over the book problems after you've solved them for homework, and please be sure to be there and follow along. Okay, have a good day.